Hello everyone, this is Dr. Sachinandan Datto, and in this video series lecture, basically the practical video series lecture, we'll learn one by one the population dynamic to the length relationship and any other different parameter, the stock estimation, and all the related practical topic of the fisheries management. So in this lecture, today's lecture, I will talk about the length-weight relationship. So length-weight relationship is a very important parameter or important analysis to understand the health or the condition of the fish, or we can also determine the length in terms of weight, or we can determine the weight in terms of length, and this relationship gives us a good idea about the fish species as well as the health of the species and also the health of the ecosystem. So before going to the practical search or practical analysis, we just learn a little bit theory of the length of relationship. So length of relationship is a calculation of basically it's a non-linear function. So here W is equal to A into L to the power B, where W stand for your weight and L stand for the length, and the unit is as per your measurement. You can put your unit length in centimeter or millimeter, whatever you want, or weight in grams or whatever you want. And A and B, these are the two functions, that A and B. So B is basically the exponential describing the rate of variation, how much is varies length in terms of weight. So it varies in weight with respect of length. And so this is a very good parameter by estimating the B will see later. And A basically denote the coefficient, so it's an interaction between length and weight, and A denotes the coefficient of the length-weight relationship. So this is a non-linear function, and if we go the linear function of this, if we make the linear function of this relationship, then we have to make it log transformation. So that linear function of this length of relationship, we have to make it a logarithm. So log of both sides, so log of W, log of weight is equal to log of A plus B into log of length. And the idea is that to estimate the B value. So B value is a very important parameter. If B in general, the in basic, the ideal value of B is 3, and that 3 value is basically it gives represent the isometric growth. Isometric growth means in respect to length, weight is increasing on a same proportion. So if the B value is less than 3, then this means that the species are much more slimmer, means the weight is not increasing in respect to length. And if the B value is greater than 3, then it's a good sign or say good condition of the fish, means in respect to length, weight is increasing very good, better than the length. So it's a positive element you can call if the B value is the greater than 3. So this is the basically theory of the length relationship, and let's check the two way of to calculate the length relationship. Here we have a data set of length and weight of the species, that is the Indian oil sardine, and here we have a very few data, almost 68 data set we have length and weight. So here length in millimeter and weight in gram. So we'll check both the function. We will check the non-linear function of this relationship, and we will also check the logarithm or the normal regression, linear regression of log transformation of this same relationship. So first we will make the log function of the length and weight both. So log of weight and log of length, make it log of length, and log of weight. So it's a very simple. We'll take log as it is 10, so log 10 of your length, and just simple clicking you will get the log of length. And log of weight, so you take the log 10 function and click the on weight, and you get the log of weight. So here the log length and weight we have already calculated, so its length is transformed into log and weight. So first we will check the non-linear function. Basically it's a power function, so L to the power b, so it's the power function. So we'll check the length. We select the length and weight of the data, and then we'll just plot it in a scatter plot. So simple scatter plot, and then you put your equation, and this equation is linear. So we have to make this linear equation into a power function. So you just select the regression line, and that double clicking by regression line you will got the trend line different function. So as in general it's normal, it's linear, but we have to make it a power. So clicking on the power, it's converted into power function. So you check the values, then you can I'll just make it a little big. So here, okay, you check the value. So we got the relation. So here y is equal to your weight, and a is your that means 4 to the power 0 means 0 to 6 means 0.6 times 0 to 4, and your b value is 3.1478. 3.1478. That means your b value is greater than 3. That means that the piece is positively isometric or positively allometric. It's not isometric, sorry, it's positive allometric. So that means that your piece of this species is length is weight is increasing more than the length. So it's a very good condition, and this is the normal or the non-linear function, the power function, and we'll check the log function now. So select the log length and log weight, and then put the same scatter plot, and we got the log length and put the equation on it, and this equation is linear, so no need to change into any other form. So it's, as we know, that the log transformation is the linear transformation. So here you got the value of b and a. So this is basically y is equal to mx plus c. So intercept and slope we are getting here, but here, yes, so your weight is equal to 3.1478, that is the b, into x means your length, and minus that function is the a. But in this transformation, this is not the a, so this is the a bar. So a dash or a bar. So a dash is your, and here is your b. So a dash is your minus 5.3749. Now you have to make this a dash into a. So a is equal to exponential of your this value, okay, or exponential of this value. So this is your a value, or you can get the exact value. So here you can make a is equal to 10 to the power your a dash. Yes, so this is the value same to the normal non-linear function. So this is how we can calculate the length weight relationship, or we can estimate the b value. So here we are just making a little modification of the graph. So we are making this border into 120, and it's 130, make goods, and you just make this axis into 15 to make its good look. Okay, and you put the title. So title is the same of this one, length relationship of, yes, and you put the axis title. Axis X is your length in millimeter, and your Y is your weight in gram. So here we are almost making this. Okay, so now it looks good. So same way you can make this graph also. You can modify this thing. Okay, so here the axis title will be log length, and here the Y will be log weight. You just make this into 1.2. yeah, now it's look good. And from this relationship you estimate two things. One is that you can tell that how is good health of this species. Here B is greater than 3, so it's an positive allometric. Positive allometric means it's a good condition and the growth is very good. And on the other hand, if from this relationship you also calculate the weight. If you don't have the weight, if you have the length, then you can predict the weight, or if you have the weight you can predict the length. So this is all about the length relationship. In the next lecture we'll see the different other population parameter one by one. Thank you.